talk a little bit about software-defined servers. Software-defined servers, I think you're going to be, if you're not familiar with it, pretty amazed by it, and hearing about it is even better when you have that wine in your hand. Let's talk about the problem, the industry challenge first, though. The industry challenge, every business is being driven by data. It's core to our businesses. We got to find a way to really maximize the value of that data. That's getting more and more of a challenge, though, because CPU and system performance isn't keeping up. Moore's law is dead. We've seen over the past 10 years that we have a 50x growth in data, 5x growth in CPU performance. So what do we do about it? Well, to maximize data, we need to keep it in memory. Why is in-memory computing important? Why is it critical? Because DRAM is 1,000 to 10,000 times faster than the fastest flash storage. So if I tell my wife, oh, honey, I'll be an hour late, she's probably annoyed or saying, yeah, again. But if I say, honey, I'll be home in a year, that's a bigger problem. And that's the exact same difference to a CPU. Okay, so we want to keep things in memory so that we can get the most out of our processors. Now, what do enterprises look for? We've been talking to all of you. Scalability, flexibility, and reliability are certainly key themes that continually come up. And you're going to hear how we're addressing these themes. So what if you could deploy a system of essentially any size in a matter of minutes? Guarantee that that system would be right-sized for the lifetime of the deployment, and have it be more reliable than you've ever seen before, avoiding 90% of the failures. And when a failure does occur, be able to recover at an unprecedented rate, at least 10, maybe even 100 times faster than what is currently possible. And keep these servers up to date with zero downtime. That will help keep them more reliable, but even more importantly, more secure. And then finally, have it where that system continues to get better over time through the power of software, the power of innovation that continually be brought to keep the system updating and getting better, and accomplish all of this at a lower cost. Okay, so introducing TidalScale. What we do is we take industry standard building block servers and combine them together to create a virtual server, a software-defined server of essentially any size. Like traditional virtualization, runs on standard x86 processors connected with Ethernet. No changes to the operating system or the application, and these can be created in a matter of minutes. So really, if you think about it, for the first time, we're able to size the computer to the data. Okay, we want to get the most out of the data. How do we do that? We have a right-sized computer, and now we can size the computer to the data. And we have an amazing group of customers and partners that we are working with as we continue to bring our technology to market. So the value proposition goes around several themes. The first theme is around scalability. We are able to scale up using scale out as one way to describe it. We are able to get in-memory performance out of these systems because we're creating a system that has all the memory that is required. And that's so key from a performance standpoint. It's also incredibly flexible. These can be created in a matter of minutes. They can be changed inside as required. They can run whatever workload is needed. So if your needs switch from one type of workload to another, you're not stuck with a proprietary fixed system, and you can adjust. And all of this can be done both on-premise as well as in the cloud. And then this new capability that we're bringing out, in fact, we just announced it yesterday, is around a new level of reliability and uptime, and specifically adding 2 nines to your system uptime. So we help avoid failures, we recover faster when a failure occurs, we allow the system to be maintained and updated with zero downtime for most maintenances. And then finally, all of this is done while driving down cost. We do that by simplifying. Simplifying allows us to reduce the CapEx and OpEx, it helps to reduce the licensing costs, and you pay as you grow. So the use cases and the customer examples are numerous. I've highlighted just a few here around both Oracle and HANA. We could have picked ones around SQL Server or Sybase or KDB or other applications. And in the bottom right, you see Jana. Jana will be our final speaker today, and you'll get to hear his story and the success. But what the common theme is that people are able to deploy faster, they're able to simplify and reduce cost, and they're able to meet their performance requirements. And now they're going to get it at a new level of reliability. Okay, so I've mentioned numerous times how you can deploy a system in minutes. I'm actually going to go through and show you how that is done in this demonstration. So here you can see this is our Wave Runner software. This is the GUI for it. You can see that we have 4 software-defined servers with 24 nodes and a total of 960 processors that are out there. And what we're going to do now is we're going to create a software-defined server. Okay, so the first thing you do is you name it. The next thing you do is you select the nodes. That's 1, 2, 3, and 4. Okay, at that point, we go and check what storage is going to be used for the boot disk, and then you choose the operating system. Here, SLES was chosen. And we're going to power on the software-defined server. So here, these systems are communicating with each other. They're querying each other, making sure all the resources are correct while the system is booting up. And at that point, a software-defined server is ready. Now we can start the guest. So we're going to start SLES on top of it, and you can see that it powers up. And in the end, what do we have? We have a system with 4 nodes, 160 CPUs, over 5 terabytes of memory, and all of that was done in a matter of minutes. Now, obviously, that was sped up. Watching servers boot is not the most exciting thing in the world, but that's about a 5-minute process that we just went down to about 40 seconds. So it is very, very fast. And that was an arbitrary size. We could have made it bigger. We could have made it smaller. We could have chose different servers, but you can see the magic of using these industry standard building blocks to create a right size server. Now, let's talk about where we're going, or actually what we're now bringing out with our 4th generation of software-defined server technology. We've gone from just proving that this could be done, making a system out of multiple different computers, having it operate like a single system. Then we got into where we could do on-premise production and brought in the Wave Runner GUI. With 3.0, we brought in a new level of features, particularly around enterprise features and scalability and performance. And with 4.0, we're bringing in a new technology that we call TidalGuard. TidalGuard is what is bringing through this breakthrough capability around uptime. We're going to go through a bunch more detail on it. Now, in addition, there's a whole new level of system monitoring that we're doing. We've simplified the deployment. We enhanced the scalability and performance as well with this release. So let's talk for a moment about where we are with our vision about where we're going. Our view is that all systems should be self-optimizing, self-healing, and self-sizing. Now, these attributes exist today in the world of networking and storage. I would argue that they've been here for decades for these particular capabilities. But when you talk about standard computing, they really don't have it, particularly when you're talking about enterprise workloads. But with TidalScale and our software-defined server technology, we have self-optimizing. That's what we accomplished from the very beginning in our first releases of the software, where we embed machine learning into our product, where we're doing machine learning to have it continually be self-optimizing to get the most performance possible. We now are bringing out self-healing, which I'm going to go into, and later this year, we will actually introduce self-sizing. So it's a very exciting time for software-defined servers. Now, why are we so focused on this reliability? Well, we're talking about running high-value workloads. The corollary, if you're running a high-value workload, is that if it's down, it's going to cost you a lot. In fact, 98% of firms say it costs them at least $100,000 per hour. And what people don't understand is that this isn't only for your systems that are running production workloads. Development and test, that can be critically important as well. We were talking to a customer last week that for their really big systems, they had over 700 developers running on those systems or on that system. And so if that system goes down, which it does a lot, the cost is extremely high. Now, we all hear about nines. I need 4 nines or 5 nines, and 85% of corporations say they need a minimum of 4 nines. Now, most people, I don't really think, know what 4 nines means. 4 nines means you have 53 minutes of downtime per year. 5 nines means you have 5 minutes of downtime per year. The reality is you can't do one maintenance update where you take a system down, where you go and do the updates and the patching, boot it back up, bring the application back up, and do that and still accomplish 4 nines. So it takes longer than that. So it's a challenge that needs to be addressed, and that's what we're focused on. Now, in addition, let's look at where hardware failures occur. Hardware failures occur, which are the number one failure mechanism for an application, is that the underlying hardware fails. The hardware failures basically fall into 4 primary categories and then everything else. There's DRAM, power supply fans, networking, storage, and as I said, everything else. The result is that what we want to do is be able to take the warning signs, because all of these give you time to act. The question is, are you able to do something about it? And the answer is obviously that would be ideal. Now, this issue around server reliability is actually getting a lot of attention. The New York Times on February 7th put out an article, Tiny Chips, Big Headaches. And they highlighted a lot of things in there around it, including what's going on with DRAM and challenges around reliability there and other issues too. But they highlighted that one widespread response is demand for new kinds of software that proactively watch for hardware errors and make it possible for system operators to remove hardware when it begins to degrade. And then there's one company that's called out for doing that, and that, very proud to say, was us, and highlight that it's a little bit like changing an engine while the airplane is flying. Now, why do we talk about this in the end? Why is this getting to be a bigger problem? Well, in 2009, Google put out a very prominent paper highlighting that DRAM had become the number one failure point in a server. Now, we all knew that it was going to get worse. It's been talked about as the geometries shrink and the physics are getting very, very challenging. But that was highlighted, and it is getting worse, by AMD when they highlighted that the DDR3 to DDR4 generation of technology, the reliability dropped by a factor of greater than 5. And that was all things being equal. But things aren't equal. We're putting more and more memory in the servers. In fact, 10x or even 20 or 30 or 50 times more memory today than we were a decade ago. But the underlying mechanism for a failure is the same in a system that has 16 gigabytes of memory or 16 terabytes, 1,000 times more memory. A 2-bit error in the wrong place will cause either failure to have what's called an uncorrectable memory error, and that is otherwise known as a system crash. Now, to make matters worse, Intel processors in the scalable generation 1, 2, and 3 of the scalable processors actually reduced the error checking and correcting capabilities available to the industry. So the problem is bad in 2009, but it has gotten much worse. We would think it's even up to 100 times worse. Okay, so TidalGuard. This is our new technology. What it allows us to do is, in this case, you'll see we're going to boot up 4 servers. We're going to create a software-defined server out of them. And on top of that, the application workload is running. And it's running in a performant fashion. Now, what happens when you get that warning sign? We have ECC errors that are showing. Well, we can actually bring in a spare, expand the software-defined server to include that spare. So we grew the system in its raw capabilities, and we begin migrating the resources off of it, the vCPUs. We push it, and then they pull the pages of memory they need. They pull the IO. All of this is done in real time using the machine learning to figure out where is the right place to put this, and all of that is done. When it is completed, we can now take that system, power it off, remove it, and that is what we call TidalGuard. It allows for the hot swapping of a server while the application was performant. Okay, so the benefits of it are widespread. It allows us to have the highest availability. Why? Because we can detect failures and avoid them. Over 90% of the failures we can detect and avoid. Next is when a failure occurs, we can recover much faster. We say have a spare available. That spare now can be booted up when a server goes down, and you basically replace it and boot back up in a matter of minutes, versus having to do the repair, the diagnostics, get the spare part, whatever, and do that before you can bring the system back online. And then it's around serviceability, highest serviceability. Why? Because we're able to take systems off proactively out of service, patch them, update them. This could be hypervisor patches, or updates. It can be driver updates. It can be firmware, BIOS, microcode, or even hardware itself can be changed out and then bring the system back online. So all of this adds up to adding at least 2 nines to system uptime. Okay, so let's look at a quick demo of what we do with this technology and how it works here. So we have the system that is up and running, and now you can see a couple of warnings that have come up here. We're going to see the system that has a warning. There's ECC errors that are starting to show in it, and we're going to say, we can't afford to risk it. Let's get that system offline. We choose swap, we choose which system we want to swap with, and then we go ahead and start that process. Swap has been initiated, and what you'll see in the top is that it's gone from 4 nodes to 5. So we've actually added the server, added the resources of that server, and we are now migrating off. Again, we push off resources like the vCPUs and let them pull the pages of memory that they need, because they will pull it exactly as they need it in exactly the right order. All of this, again, is happening in real time. Migration of resources is something that we do constantly. It's a part of our built-in architecture of a software-defined server. We're now just using it to allow us to basically hot swap this system. So you can see it's 80% progressed. When we get to 100%, you're going to see that the 5 nodes is going to drop down here to 4 in just a moment. There it is, but down to 4, and it is complete, all while keeping the application performant. So anyway, that's what we're doing with this breakthrough capability that we have just introduced in our 4th generation technology.